Hello students, welcome to the lecture number 9 on hydrocarbon chapter. In this chapter, we are going to discuss a very important hydrocarbons, that is aromatic hydrocarbons. So far we have discussed different types of hydrocarbons that is basically included in your syllabus, that is alkanes, alkenes and alkyne, and we have covered those things that is syllabus, like your preparation of all those hydrocarbons and its physical and chemical properties. In this lecture we are going to discuss that is the aromatic hydrocarbons. So this is K.K. Mukherjee, the Science with Mukherjee Sir YouTube channel. First let us understand, that is the heading of this lecture, that we have said, that is aromatic hydrocarbon. Why it is called aromatic? First let us understand. Aromatic means that these hydrocarbon, if we compare with the other hydrocarbons, that is alkene, alkyne or alkane, those hydrocarbons are basically odorless. There is no smell you can find in those hydrocarbons. But in these aromatic hydrocarbons, what you find? You will find that is a pleasant smell. Basically, the word aromatic comes from the Greek word aroma. Aroma means sweet smelling. So why it is called aromatic hydrocarbon? It is now clear that it is basically due to its sweet smell. Majority of the aromatic hydrocarbons, majority I am telling you because not all, it is having a benzene ring. And the benzene ring, you can see, you can observe later on that it is very much, in spite of this fact, it is a unsaturated one, but it is very much has been found to be stable. During any chemical reaction, you will find that its unsaturation has been retained, and due to its special properties, normally what is going to happen, the unsaturated compound, that what we have observed in case of alkene or alkyne, that they will readily undergo the addition reactions. But these aromatic hydrocarbons is not going to show this property in normal conditions. Of course, they will show this property under a drastic condition, but that will not going to call it its chemical property when it is being carried out in a drastic condition. So its preference is basically, you will find, that is the electrophilic substitutions. It is preferred for the electrophilic substitutions than addition reactions. So these two very important property of this benzene, that this aromatic compound, that what we find, that its unexceptional stability, unusual stability, and second thing that it is having, that is that it do not undergo the addition reactions like other unsaturated hydrocarbons. So these are two special things, and in this lecture we are going to understand why it is so that this type of things happens to these aromatic hydrocarbons. There are some aromatic hydrocarbons which do not contain any benzene ring, and some aromatic hydrocarbons which is having the benzene ring. So we can write here those aromatic compounds which included the benzene ring. It is called the benzoate. This is called benzoate. Benzoate means that it is aromatic compound having the benzene ring. So we can write it. It is aromatic compound having benzene ring. This is called benzoate. The example of this, benzene itself, the parent aromatic hydrocarbon, this is benzene. Then another aromatic compound, that is a very important compound, that is naphthalene. This is another benzene compound, it is called naphthalene. Naphthalene. Another compound, this is anthracene. Or another compound, we can say this is biphenyl. So these are all benzoate because it is having the benzene ring. You can see here it is benzene ring. You can see there is a 2 benzene ring. You can see 3 benzene ring, and it has also a 2 benzene ring. So they are aromatic compound, but its class is benzoate. Another class of aromatic compound, this is called non-benzoate. It is an aromatic compound also. This is also aromatic compound. Aromatic compound having other ring system, not benzene ring, having other ring system, other ring, not benzene ring. Example of this, this is pyridine. This is pyridine. Pyridine you can use, you see the application. It is a very strong base, and that has been used in very reactions for different type of purposes. Benzene ring. Then another, this is pyrrole. Sorry, this is pyrrole. This is pyrrole. Another type, this is thiophene. Thiophene. Another, this is pyrrole. So these are all non-benzoate. Why it is not benzoate? Because it is having the ring. This is having the ring, but this is not a benzene ring. But its property matches with the aromatic compound. The basic property that we have already discussed, that it will have very stability and it will do not undergo the addition reaction, rather it prefer the electrophilic substitution reactions. So now we understand the basic aromatic hydrocarbons is basically those hydrocarbons which is having a very good smell, very sweet smell. Those are called the aromatic hydrocarbons. Why it is called aromatic? Because this name aroma, that is from the Greek word, aroma means pleasing. and it has a special characteristics that it is high stability and it is having, it do not undergo the addition reaction like other unsaturated compound. In most of the reaction you will find that benzene retains its unsaturation during the chemical reactions. So this is the things that were discussed. Now we are going to discuss why the structure of the benzene ring, and from this we will go why benzene shows such exceptional property as compared to the other alkene or alkyne or alkane. Okay, structure of benzene. Benzene was isolated by Michael Faraday in the year 1825, and he observed its chemical formula is molecular formula is C6H6, which tells us about the high unsaturation point of this chemical. So this tells us that this is highly unsaturated. Understand? So, and it has been already we have discussed that it is not correlated to other alkenes or alkanes, other hydrocarbons, alkenes or alkynes. Where you find that its formula is different. So here you can see its molecular formula this and this, and benzene having the special property that we are already discussed, that it is having the high stability, number one, and number two, that is it is unique properties. So this is two properties, that is two things that we are going to discuss, that is high stability and unique property. Alright? So when it forms, another thing that we want to say, that it forms triozonate. Benzene forms triozonate. It's formed triozonate when with the ozone, when we react with the ozone, which tells us that presence of 3 double bond. Presence of 3 double bond. Number 3, that is 1 point, that is E. B point is, it's when there is a monosubstituted compound, it only form one monosubstituted product. Only form one monosubstituted product, and from this what it signifies? It signifies one very interesting thing, that all the carbon atom and hydrogen atom present in the benzene is identical. That is why it only gives only one monosubstituted compound. And from the other experimental evidence, in the year 1865, Kekulé proposed the structure of the benzene as a cyclic arrangement of carbon atoms in a regular hexagon, and it is a planar structure, flat structure, and it is having alternate double bond and single bond, and all the carbon atom is bonded to the other single hydrogen atom. So what Kekulé structure says, it is like this. This is the carbon atom, each corner of the hexagon, regular hexagon. This is regular hexagon. You see that is, there is a carbon atom. And this carbon atom having the alternate double bond, single bond, double bond, single bond, double bond and single bond. And each and every carbon atom is having the hydrogen atom. This is the structure what is proposed by Kekulé after researching different types of properties. Like this, it is formed triogenite. Then he observed that it only formed the only one monosubstituted compounds. From this, he is able to give this structure, that is this, and it has been also been written in this way. This is like this. So this is the structure of the benzene proposed by Kekulé. Okay. Now, if we go by the Kekulé structure, what is going to happen? There should be two disubstituted compound isomers, two disubstituted compounds. What are those compounds? Let us see. One compound disubstituted, we are not talking about the mono, disubstituted this. Suppose this is bromine, 1,2-dibromobenzene, suppose. Or another isomers is possible as per Kekulé structure. Theoretically, we are saying theoretically, not practically. This, in the one case, you can see the bromine atom has been joined to this carbon atom which is bonded double bond, which is having the double bond, and another case it is having the carbon-carbon single bond. But practically what you observe? Practically observe this only one 1,2-dibromobenzene. Only one, not two. So to resolve this issue, what Kekulé proposed, explained, that he says this double bond is vibrating. He says like this double bond. This double bond position is changed, which means this double bond will be here, and here. So the position of the double bond is changes, and that is why you will find this only one compound. But these do not able to explain many other properties. Number one property that we have discussed, that is its high stability, and second thing is unique property, that it is preferred, that benzene preferred to give, benzene or any other aromatic compound preferred to give the electrophilic substitution reaction than addition reaction. And we understand that in other previous section we also observed that alkene or alkyne, they can readily able to give the addition reactions. But here it will not going to undergo the addition reaction, it will show the electrophilic substitution reactions. And this cannot be explained by this K-Cooling structure, but we will now going to explain it with the help of the valence bond theory. Is a hybrid of different resonating structure of the benzenes. Different resonating structure that we have already discussed, the K-Cooling structure, that the main contributing structure. This structure is going to contribute a hybrid structure, and this is actually the structure of the benzene, not all those K-Cooling structures. So let us understand this. What are the K-Cooling structure? This is suppose A structure that we have discussed. Another structure is B structure. This is basically two structure. But as per resonance, these actually are not the actual structure of the benzene. Actual structure of the benzene is basically hybrid of these two structures, and this is basically this. So when we are representing the hybrid structure, how do we represent? We represent with this dotted circle or this circle. This circle signifies that the delocalized pi electrons, and this delocalized pi electrons that we later on understand is the main source of the higher stability of the benzene aromatic compound. Whereas K-Cooling has made the structure like this. He has made this double bond as a localized. That is his drawbacks of this structure. He made this double bond is localized. K-Cooling has made the double bond localized, but actually it is not localized. It is delocalized. It is encompassing, or we can say revolving around all the 6 carbon atoms, and that is why this has happened. Because you can understand easily, if it is correct, suppose K-Cooling structure is correct, means it will have that double bond, single bond, double bond or single bond. But if we measure the distance, bond length of this benzene ring, bond length between the carbon-carbon, what we find? We found it is same. The bond length is same. So you can write bond length. Bond length is same. And what is that bond length? It is 139 picometer. But if it is double bond or alternate double bond or single bond, what K-Cooling has proposed, it should be 2 bond lengths. Bond length will be 2, and that is the reason behind this resonance. What resonance tell? Resonance tells us actually these structures, these Lewis structures, do not going to give us the right picture about the structure of the molecule. But if we go by the resonance, we can able to understand what is happening there. So bond length is same 139 picometer, whereas if we go by this, its bond length will be double bond, as the bond length will be 133 picometer, whereas single will be 154 picometer. And what we actually find? Actually we get 139 picometer. So if we understand this, actually this is not a true double bond, and that is the reason it is not going to show the addition reaction. Because in the addition reaction, what we observe in the alkene or alkyne, that electrophile will easily be attracted because those are loosely pi electrons that can be easily available to these reagents, that is electrophile. But here it is not like this. And this can be further be understood if we go the orbital overlapping, that is the base of the valence bond theory. Orbital overlapping, you can see, for that we have to understand the structure of this benzene ring. Benzene ring, we know, have this structure. This is regular hexagon. Here you can see this benzene ring. You can see here on a very important thing that there is 6 carbon atom in the benzene. It is sp2 hybridized. This is sp2 hybridized, and it has 3 hybridized sp2 orbitals. And these 3 orbitals, 2 of these orbitals will make sigma bond with the adjacent carbon atom, and another is make the sigma bond with the 1s orbital of the hydrogen. So here you can see 6 sigma bond, 6 single bond, that is sigma bond. Okay, we are not drawing the hydrogen for maintaining the simplicity of this diagram. So now what is happening, as because it is sp2 hybridized, so every carbon atom is left with 1 unhybridized orbitals, 1 unhybridized 2p orbitals. So we can see this is one unhybridized orbitals. As we know, this will be perpendicular to the plane, of this regular hexagon, that is the plane of the benzene ring, and this will be perpendicular to this all orbitals, that is unhybridized orbitals are perpendicular to this regular hexagonal plane. So here you can see this unhybridized orbital will make a pi bond. How they will make a pi bond? Now they will overlap laterally. Here the overlapping is done end to end. Here it is laterally. So what is there? What is there in the 2 ways they can overlap? In the one way is this. These 2 will overlap this. These 2 will overlap this way, and these 2 will overlap this way. So this will form this capule structure. Here this, here double bond, and here double bond. Okay, but this can be otherwise. Otherwise, this can be like this. Again, we are drawing this to make you understand. Now, this overlapping can be done in the other fashion also. This way can also overlap. This will also overlap. So in this case, structure will be this. Double bond will be here, here, and here. So the overlapping of the orbitals will be other ways. That it can be overlap this way, it can overlap this way. So what we observe as because it is in the perpendicular, this is the plane, and the plane there is a perpendicular. This all the unhybridized orbitals are perpendicular. So what we find, suppose this is a plane of the paper, just you understand. Plane of the paper. Here in the top there will be one electron cloud and the bottom there will be electron cloud. Means these electrons are totally delocalized. It is encompassing all the carbon atoms, all the 6 carbon atoms. It is not like that it will only remain here, here and here, here and here, or here and here. That we observe in case of alkene or alkyne. There it is a open chain and the double bond will be situated between these 2 carbon atoms or these 2 carbon atoms. They are called localized. Here it is not localized because it is a cyclic one and it is a planar one. So what is going to happen? There is a delocalization of the pi electrons. And this delocalization of the pi electrons, what is going to happen? This every carbon atom will attract all those electrons, 6 electrons. So they will be firmly bonded to all the 6 carbon nucleus. And as a matter of fact, what is going to happen? There will be less available for bonding because the electrophile will not able to take up all those electrons because it is occupied, it is firmly bonded to all these 6 carbon atoms, and that is why it is stable. Understand? The reason of this, it is stable because of the delocalization of the pi electrons. So actually the double bond, what we are telling, double bond, it is not actually a double bond, it is a in between, not double bond, not a single bond. It is not a purely double bond, and that is why it is not going to show the addition reactions as the alkene or alkyne. So hope the point is clear. The basic aromatic property that when we call a product is aromatic, when it is very much stable, unusually stable in spite of these unsaturations, and it also do not undergo the addition reaction, and it has a good smell, pleasant smelling, then we call it the aromatic. And we understand in this lecture, that is what do we call it is aromatic, number 1. Number 2, we discuss what is benzenoid, what is non-benzenoid. Then we discuss the structure, the development, evolution of the structure, how it has been isolated by Michael Faraday, then on the basis of different types of experiments that were done by different scientists, and their properties has been assigned, and it is going to create the primary structure of the benzene. And afterwards, with the help of valence bond theory, that we are able to understand why the benzene is exceptionally stable, that is the aromatic compound is exceptionally stable, and why it do not show the addition reactions, rather it favor the unsaturation and the electrophilic substitution reactions. So that is all for today's lecture. If you like this lecture, you can share to your friends, and hope that the points are clear to you. In the next lecture, we will discuss about the aromaticity. When we call a compound is aromatic, there is a very 3 technical terms that we are going to discuss in the next lectures. Till then, all the best and be best, and thank you for listening.